transportation, sustainability, and climate change, and data analytics. So a lot of very, very interesting areas. So today he's going to give a talk particularly about the more quantitative side of on-demand additive manufacturing. So we were fortunate to be able to get him on board and give us this talk because he's among the very few researchers in the country that actually got into the numbers of additive manufacturing. So within our department, additive manufacturing is a very unique area. Traditionally, it has a lot to do with materials, with structures, with processes, and is considered to be more of a mechanical engineering and material science. But in the recent years, many of you have probably already heard about a lot of the advantages in the supply chain systems and logistics utilizing additive manufacturing. But unfortunately, so far, most of these discussions and publications are more on the conceptual side. And so Dr. Jing has been one of the few people that have really looked into the number part to actually say, okay, additive sometimes makes sense. This is what the numbers look like in terms of cost and lead time and supply and the demand fulfillment, so on and so forth. And I think this is something that we all need to have a better appreciation of. So hopefully you enjoy today's talk. And feel free to put your questions either in the chat box or until after the presentation. So with that, is there anything else you wanted to add to Dr. Jing?
No, not really. So thank you so much for the introduction, and also thank you so much for inviting me here to give a talk about my research. So thank you. So for the audience, okay, if you have any questions, please just feel free and ask.
Okay, it's a privilege. So it's all yours now, Dr. Jing.
Okay, thank you so much.
Feel free to take over.
Yeah. So today I will just talk about additive manufacturing, and especially for supply chain management. Okay, so we actually, my group has several students who are working on additive manufacturing. So including, something, Dr. Liang has already mentioned more like concept kind of things like quality, anomaly detection, and also decision making. And so Ray, a PhD student, is working on that with Oak Ridge National Lab. And Jeremy Hill is working on additive manufacturing AM machine monitoring. And that project is funded by Y12. That's another DOE facility. And also we were funded by American Makes, working on AM productivity. So Hossein Kos, he's another PhD student. He's working on how we can basically reach the trade-off between productivity and also quality. But today I will talk about AM business adoption. So including like cost model, part choice, and capacity planning, and also AM supply network design. So that work was mainly done by Tanner Kokoyasa. He just graduated. Right now he is a postdoc at Argonne National Lab. But right now he's working more on transportation problems over there. The other three students will graduate in this year. So now let's just talk about that. Okay, we will focus on this. So my talk will have two parts. The first part is more about a single location. So mainly, this part is for small, medium, or kind of companies. They just have one location, and we try to understand, should they adopt AM, and if they adopt AM, which parts should be produced by AM, or some parts perhaps still should be produced through conventional manufacturing, we call it CM. So we will use some queuing theory, basically multi-class MGK queuing theory, and also there are also some inventory policy like S-1S, and we build a mixed integer nonlinear program and then develop some of the heuristics. The second part is perhaps for bigger enterprises. They may have multiple locations, so that then the question is how can we decide a network to deploy AM capability. So let's just start from the first one. Yeah, I already mentioned that. That's just very brief kind of introduction. You perhaps know that now more and more enterprises and also organizations now have already adopted AM, including like U.S. Navy and Airbus, Boeing, Toyota, and also BMW. So typically we really mainly focus on spare parts with low demand. In other words, the demand rates are relatively low. So as you know, from the inventory management viewpoint, spare parts with low demand are hard to manage harder to manage for inventory because the demand doesn't happen very often. So you cannot really use traditional like EOQ model or RQ model. So S-1S inventory policy is a very kind of common model for those kind of things. Just because the demand is low, so when you use one, you basically place an order just with one unit. So that's a traditional model. The model has already been here for many, many years, I think. The model was mainly developed in 1970s. And so now, we have AM. So the challenge for spare parts with low demand, key here is that low demand. So in many cases, items could be in inventory for a long time and not used. So AM provides another option. So not necessarily we have to keep inventory for many, many spare parts. We perhaps can just print one part once it is needed. So that's one possibility. I don't know how much you know, AM, but in general, AM has several features that we may consider from the supply chain management viewpoint. One is that, typically one AM machine is more flexible. So one machine can be used, to produce many different parts with pretty shorter switch over time. And also the cost could be high, could be low. It really depends. If you want to produce, a large quantity, then the cost perhaps is higher than conventional manufacturing. But if you just want to produce one part, then the cost for design and also for the design and also setup of the machine will be much lower for AM compared to conventional manufacturing. So also, as you know, AM can handle pretty complicated geometry and also can even use different materials. And for single part, the lead time could be short, and also we have a lot of freedom for design. So we are trying to incorporate those kind of advantages and also features of AM in the model. So now just think about one part. Now we have two options. We can either keep an inventory on site. When we need it, we just use one from the inventory. Then we also place an order from some traditional supplier. And another way is that when we need a part, we just print it out. We don't hold any inventory. So obviously, both options have some advantages and also disadvantages. If we have a look at inventory option, of course it's very, very kind of high responsive. So when you need it, it's there. It's already in the inventory, right? So you can get it immediately. And if you can buy it from the market, typically the part price is low. But there are several disadvantages because the demand is very, very low. So the inventory holding cost is much higher. And if, especially the part is not available in the market, and it could be, a big problem for many older systems. So if you talk about like airplanes, many airplanes actually perhaps were designed and also produced 40 or 50 years ago. So at this moment, those parts, many parts just don't have a good supply base. So you just, even you want to find them, sometimes it takes a lot of time to find one, or maybe you just cannot find it from the market at all. So when there's a stock out, the lead time for getting one is very, very long, and the cost is huge because you even may not have the design. You have to replace one part, but you cannot find the design. But if we use the AM option, of course, you don't have inventory, right? and but you will have some production costs, and one machine can be used to produce many parts, and also you don't have a translation cost because you printed that on site. But the challenge is that typically still the build time is long, could be from hours to weeks, depending on materials, depending on technologies, and also the parts. And at this moment for metal AM machines, so the cost is still very high, could be around $1 million. So for some businesses, it's still a big capital investment. And another bigger issue is more about the quality. So at this moment, AM still has some quality issue, and so we also have some other students working on the quality. So these are kind of two options. And for this problem, actually, Song and John published one paper at Management Science talking about how to make the choice between these options. And actually, we will start work on that pretty many years ago, 4 years ago, but we are so slow in writing the paper because of one author. He's from business school. He's great, just he's also busy. So they definitely, we didn't know their paper when we started work, but anyway, they published a paper at Management Science. And also our papers are still different because they only consider one AM machine. They don't worry about machine capacity. And also they only use one heuristic to solve the problem. And we definitely consider multiple machines, and also the model settings are also a little bit different, especially for the queuing part. And we developed some exact solution algorithm. There are some other recent papers from EGOR, and the second paper even has not been published, but it's okay. But they are kind of different things. They usually have looked at part quality a lot, try to model that. And also the third paper is more about, because of the quality concern, they suggest that, when you need a part, you just, use an AM part temporarily, and during the lead time, basically when you get, our standard part. So here are kind of, that perhaps could be a challenge for students. So here just, a little bit of assumptions and notations. So we now assume that, we have a set of, products. So here is P. P is a set of products, and small p is its index. And A basically is a subset of products that will be produced by AM. So A, of course, is depends on the decisions, and then it's a subset of P. And I is set of products in inventory, and K is possible number of AM machines. Then we have several variables. So YP is pretty simple. If we decide to use AM for part P, then it is 1, otherwise 0. K is number of AM machines, and the WQ here is a big thing. So basically that's because AM takes time, and we don't exactly know when the demand will happen. So it's more like a queuing system. For queuing system, we have waiting time. So that's kind of the waiting time for AM parts. It also depends on how many machines we have. And because we use MGK, so for MGK, not just like MMK, so we also need the second moment of the service time for a product in A. Basically, those products are produced by AM. So lambda is aggregate arrival rate for products in A, and rho, is a traffic intensity. It depends on lambda, depends on mu, and also depends on K. We also have something called zeta. You don't worry about that at this moment. Basically, it's a V times lambda. So all those variables actually are related to YP. If you choose different parts to print, it will have an impact on lambda, also mu and V and all those things. And what kind of information we need? One is of course, if we want to have an AM machine, there's a cost. Those machines are not cheap. And then we also have unit production cost for product P through AM. Then also if you decide to hold the inventory, then what is kind of the cost, the purchase cost, right, from suppliers, and inventory holding cost. And the DP here is a very important thing, because when we talk about spare parts, if we don't have a spare part available for a period of time when it is needed. It will hurt perhaps production, and it will hurt operations. So DP here is what we call the unavailability cost of product P per unit time. So of course, if we choose the inventory option, then there's a lead time for purchase, and also for product P, specific product P, we know the demand rate, we know the service rate. Okay, if service rate for each specific product P. So then also we have inventory policy SP star and PP. Those kind of things could be calculated before the optimization model. So here is basically the traditional inventory model for S-1S. So yeah, so basically if you know all kind of cost structure, you can calculate what is the optimal inventory level, SP star, and you can also calculate the expected back order kind of level. And so here, that this kind of model has already well known, and so we just adopted the model. We didn't make any contributions to the model. So this is a very traditional inventory model. But if we have look at the AM option, then it's a different story, because of course we don't have a cost model for AM options. So in that case, we have two kind of cost components. The first cost component is more about build cost. So if we have look at a specific part P, so it's a lambda P times CPA, because lambda P is demand rate, and times the unit production cost of CPA. That's the first part. And for the second part, yeah, so this one is more related to kind of lead time. And so you can see that the lead time including the build time for part P, but also it's related to the waiting time. And this waiting time is still based on MGK model. So here is basically the MGK. You can see that it's pretty complicated function. It is a function in rho and also in zeta, and also it's related to K. So, but the good thing that no matter for rho or for zeta, they are kind of linear function in the decision variable YP. So still remember, YP is a binary variable. It is 1 when we produce it by AM. If it's 0, of course, we keep inventory for that part P. So if we put both terms together and also add the fixed cost for AM machines, so that's the overall model. Of course, the challenge here is the cost. Okay, for AM option is a nonlinear function, especially for the waiting time, and also this one also is we also need to multiply the waiting time with the decision variable YP. So we can convert it and by introducing one big number M1. So basically, this is the waiting cost for part P. It depends on the waiting time and also, of course, only that cost only happens when the part is produced by AM. Okay, so we kind of change that multiplication into linear constraints. But we still have that challenge because here WP is still a nonlinear function, and as I said, of course, rho, zeta both linear already, but WP is a nonlinear function in zeta and rho. So we just try our best to also linearize the waiting time term, WQ. So that's the formulation, and we just separated them into the first part only has basically zeta, and this one doesn't have rho, and the second part has rho. Okay. And the first part, the good thing is that it is completely linear to YP, and the second part is a pretty complicated function in rho. But the good thing is that we can prove that psi k rho is convex in rho. So it gives us some opportunity to linearize this term. So because this size k rho is convex in rho, so we create some kind of cuts, valid cuts. So it's pretty simple idea because it's convex. You can say that. So at any point, if we use a linear cut, this linear cut will support this convex curve. So we kind of can just solve the problem. Then we can check whether it's feasible or not. If it is not feasible, we add a cut. Then just lift the cost term, clear this function of psi. So, and by doing that, we can add the linear cuts just one by one. Okay, and it's easy to prove that it will definitely converge. And also, we have very simple numerical example. It can converge actually very quickly. This kind of cut generation algorithm. Yeah, especially for very small cases. So yeah, here just the cut generation algorithm. We just add cuts over time. But there, if we have look at the computational complexity, it's kind of still it's 2 powered by p. Here p is the number of parts that we consider. So if we only consider like 5 or 10 parts, it's not a big deal. But if we want to have look at look at 100 or 1,000 parts, it's not possible because we will create a lot of cuts. And the convergence rate is very low. So because after we realized that problem, we also created 2 other algorithms. One is called static allocation algorithm. So for that one, we also it's more like, they are more like heuristics. So for the first one, we basically say that for some part, right? And if that part, even that part, we add that to the set of parts for AM. If the cost is still higher than the inventory cost, even there's no waiting time, and then that part should never be printed. It should be purchased and held in inventory. So that's kind of lemma 1. Also for lemma 2, we also know that for this one, so this is more like it's called supermodularity kind of condition. And so basically, when we have looked at the rho, so if A1 is a subset of A2, then definitely rho for A1, that's traffic intensity is lower than rho for rho A1 is smaller than rho A2, so no doubt. And then finally, there's a lemma 3, and also if we talk about one part, if no matter if we just include all parts to AM option, if for that part the AM cost is still lower than inventory option, then definitely we will assign that part to the AM option. So these 3 lemmas really help us to develop one algorithm we call the static allocation algorithm. Basically, we just use these 2 conditions to assign parts to these 2 options. Of course, there are still some parts, right, that do not meet each condition. So in that case, we use some kind of a simple dispatch rule. Based on that ratio, we assign the part to one of these 2 options. So it really depends on the demand rate and also how critical the part is, and AM kind of unit of production cost, and also the service rate, basically the build time for AM, and inventory holding cost and inventory purchasing cost. So when we have a look at this kind of ratio, we can kind of assign things one by one, into the AM option. So this one kind of the complexity. You can see that it's more about p times log p. So of course the complexity level is much lower. So we also have another algorithm more like Grady algorithm. So that one is a little bit more complicated. Kind of we just add one by one still, and based on the one lemma, saying that, okay, if we still have A1, right? A1 is contained by A2. So when we add one more part, of course, that part doesn't belong to A2. So that row, so basically the marginal impact on traffic intensity for part P to join A1 is smaller than the marginal impact of that part to join A2. So that's okay. Another lemma, it's pretty easy, okay, to prove. So we also use that lemma to develop another algorithm. It's more like a greedy algorithm, and it's a little bit more complicated, and but still pretty fast because complexity is p squared. So we did pretty many numerical experiments and just compare these three algorithms. Of course, the static allocation algorithm is very, very fast. Okay, it just takes like 1 second or something like that. And when we use cut generation, so typically we use Groovy to solve the MIP, then also add cuts over iterations. And for smaller problem like 50, 100, we can solve it. But when we increase the problem size to have like 200 or 400 parts, then we cannot solve it. Basically, we stop when we reach the limit of 1 hour. Then greedy algorithm kind of is between these two algorithms. And here is also kind of this, the second table is more about the solution statistics. Say, how many parts actually we assigned to AM option, and also what is the overall kind of demand rate for AM options, how many machines we will use, and also what is the traffic intensity on the different kind of cases, and what is the average waiting time for the AM machine option. So here is another kind of a figure. That's just we create that just with 100 parts. Okay. And then over here we have both triangles and stars. So for stars, actually those parts are assigned to AM, and for triangles, those parts are assigned to the inventory option. And here the X and Y, actually this one is more about the traffic intensity for one specific part. So lambda P over mu P. So first you can say that if the demand rate is very high for one part, then we will use the inventory option. So mu P is really about how fast we can produce it through AM option. If it takes too much time, we will also use the inventory option. But if we can print it out very quickly, we will use the AM option. And here is more about cost term, and the trade-off kind of among inventory holding cost, then also the inventory purchasing cost, and also additive manufacturing production cost. So one thing about the DP. So what is the DP? Basically, it's about how important one part is. So when one part is very, very important, and if we need it, we don't have it, the loss is very high. In that case, we should hold some inventory for immediate availability. But if we can wait a little bit, then we can use AM. So you can see that for this kind of square, we have like two lines. If this kind of if a part is above the first line, definitely we will hold inventory. If a part is below the second line, we will print them out. But between that, we need optimization. So we don't exactly know what's the choice. Okay. So that's also the motivation for our first algorithm, the heuristic algorithm. So how can we have look at kind of the ratio between these two ratios? So they give us some kind of guidance which option we should prefer. But this kind of ratio cannot be used to kind of classify all parts very clearly. So why we want to have this kind of model? So we also make some comparison. So for example, first case, if we only use AM option, we find that actually our optimal solution will save 42% okay, cost. If okay, we don't allow additive manufacturing, we only use okay the inventory option, then our optimal solution compared to that can save about 32% cost. And they also do some sensitivity analysis to have a look at the detail about okay how when we increase the number of AM machines and how okay the total cost and also each cost term evolves when we increase K. And here also, yeah, same story. Have a look at okay when we increase K, what's the impact on the utilization and also but no, so first one is kind of the assignment, and also row is the traffic intensity. So in general, yeah, of course, when you increase the number of AM machines and the cost overall kind of okay, has this kind of shape. So that's why we have some kind of optimal value for AM capacity. And when K increases, row will definitely increase. But it's not a good idea because when you use AM too much and the total cost will go up. Yeah, especially kind of okay the AM kind of fixed cost because AM machines are still very expensive. So we also have looked at okay some other factors. So the first figure is more about okay if we can basically improve the AM okay material cost. So here the AM kind of material cost and also AM machine cost, and perhaps okay also increase the build speed. So you can see that okay the first two kind of actually no the AM material and build rate okay are very very important. So AM technology is evolving very fast right now. So we just want to say okay if we can improve the technology, how much we can improve our productivity. And the second figure is a little bit different perspective because of course if okay we improve AM kind of technology, we want to know whether OEMs have incentive to do it. Because okay, so that's why we have looked at still those kind of three factors and say okay, how many machines OEMs can sell. So it's kind of interesting, of course, if OEM can reduce AM material cost and also reduce the machine cost, they definitely will sell more machines, right? And however, if they just okay make AM faster, yes, they basically more parts will be assigned to the AM option. However, because okay AM becomes faster and faster, and customers don't really necessarily will buy more AM machines. So actually it will hurt OEMs for their sales. So that's also a bigger problem. So we just want to see whether OEMs have incentive to improve AM technologies from the business viewpoint. So this is kind of okay the first part of my talk. And any questions?
I wanted to just jump in real quick and with about a thought that I have when you're talking about this last slide. So it's very interesting that we look at the problem from the OEM's perspective. So there are some recent progress, as you know, that tries to develop bigger additive systems with say with powder bed fusion. It's multiple laser beams, so it scales up the production rate or the building speed, but then the another paper just said the scaling factor is actually smaller than 1, which means that if you have 2 laser and the production rate is not necessarily 2 times the original 1 laser system. So that brings up the question of whether it's worth it.
That's a very good comment. I think you're talking about the band system, right? 1690 band system?
It's with powder bed fusion as well. So there are like 2 lasers, 4 lasers, 8 lasers, 16 lasers.
So you definitely need to worry about also the conflict, right? Mm-hmm. And if you worry about that, it's also a traditional yeah, traditional OR problem, right? So basically, it's a routing problem, and also you need to avoid conflict. Definitely, it will hurt the productivity. You are definitely right. Yeah, but it could be a very interesting OR problem, right, for routing.
Yeah, it could be, and just like you said, the last point there, that in some cases improving the build rate can actually reduce their profit. So, well, what would be the motivation factor for them to develop bigger systems? Now that the fact is that the bigger systems is actually not as efficient as multiple single beam systems.
You're right.
So that's just a very very quick thought that I think is worth sharing here.
Yeah, it's a very insightful kind of comment, and yeah, definitely it's true, because if we want to promote AM, we really need to worry about many players, right? From DOE's viewpoint, they definitely want to promote it, but for small and medium manufacturers, they really worry about several things. We had some workshop years ago. They talk about, of course, the cost of machines, and also the cost for people, because they have to learn something new. And also they worry about the risk of the technology development, because the technology is moving so fast. They say, let's just wait, because we know that the technology is not so mature at this moment. Why not? Just wait and don't buy things at this moment. For bigger companies, it's a little bit different. For Boeing, Honeywell, yeah, they have money, and also sometimes they want to invest for future, invest for other purposes. More sometimes the public kind of image kind of things. That's why they do a lot. But for OEM, that's another thing. Actually, many OEMs cannot really survive very well. That's also why GE bought several companies, because anyway, those companies, they heavily depend on government kind of subsidy. Otherwise, they just cannot survive. So it's a big problem, because if you want to grow it, you need to have a pretty healthy kind of ecosystem, right?
Yeah, right, which is not quite in place just yet.
Not really. Yeah, based on our kind of workshop. Yeah, so many people have concerns. Yeah, but everybody likes the idea, no doubt. Everybody likes it, but it doesn't mean that everybody wants to make real investment. That's a different story.
Yeah, absolutely. The pain of growth. Okay. So it looks like there is no other immediate questions for now. So do we wanted to proceed with?
Right. So the second part is more like so far we just talk about one location and talk about just for parts, right? How we can kind of make the decision for each part. But now we just extend it to multiple location kind of decisions, and especially for larger companies. So now the question is that where we should have AM capacity. Should we just have like one location or multiple locations? So it's more like a network optimization problem and also traditional facility location problem. But of course, we still need to worry about AM kind of things. So I have already had this kind of introduction. And also, there are, of course, many papers about these kind of issues, but most of them for AM, very, very qualitative, as what Dr. Yang had already mentioned, they are just talking about concepts. And yeah, we also wrote several papers more about the concepts, that's fine. But no really kind of mathematical models for decision making. But also, for decision making, actually, we also kind of our model structure is very similar to traditional stochastic queue media model with multiple mobile service with multiple facilities. So in 2007 by Berman and Jesman. So here, the structure is very similar to the first part, but now the decisions are a bit different because now we also have a network. So when we say, first thing, be careful, when we have a P part, we're not exactly talking about just a part, but also include that P includes the information of location. So for example, if you need to kind of get to, how can I say that, to metal parts, right? For the same metal part, if they are needed at different locations, then we have different indices. Because this paper is under revision for one journal. And yes, some review were confused by that. Okay, but anyway, so that P has location information. Then we also have like facility information. So this is a set of potential facilities where we can have AM capacity. And then also we talk about for decision variables at each facility I, one decision variable is how many AM machines we should have, and so that's all kind of things with I. So now we have one dimension of I, location. So even for the average waiting time for printing parts, now at different locations, the waiting time will be different. It really depends on the assignment of parts that will be produced by AM to that specific location. So all the things are similar, but we just have one more dimension of I. It makes the problem a little bit more complicated. And because now we are looking at a network, so we also include the logistic cost for having a part through facility I. Okay, so that's kind of logistic cost. And also we have logistic lead time because time is very, very important. So we also have that call for lead time for both the purchase and also print for the AM option. So all other things are very similar. So yeah, this slide is kind of very similar. Just talk about the inventory cost model and also AM cost model at each location I. And now the model is a little bit more complicated just because first off, now SI is a decision variable. And so we have that dimension. And it's also here. So before, actually, that constraint is a linear constraint, but now it's not. It becomes a nonlinear constraint. And so that's one challenge for us. But it's not too bad. It's pretty easy to convert that into linear kind of constraints just by introducing one more variable called SI. SI is 1 if we have exactly S AM machines at location I. And of course, that one equals to 1. And so we can have this constraint. But still, this constraint is still not linear because both X and rho are variables. But that's fine. We can convert it by introducing one more variable, phi SI, and with some inequalities. Okay, so by doing that, now we have linear functions, at least a linear kind of constraints, at least for SI. We still have that waiting time kind of things. So we do kind of similar things to separate them into zeta I and also a function. So in that case, psi I. That function depends on both rho I and SI. So yeah, keep in mind at this moment, the SI is a decision variable. So we can still prove that this convex at least in rho I. So we have similar idea just to have kind of cutting generation to add cuts to simulate the nonlinear curve. Of course, with multiple locations, the functions become more complicated, and we just need to introduce more binary variables to make it happen. But anyway, yeah, I don't think we need to worry about that too much. Just the idea is still very similar. Just add cuts one by one over time and solve it. Oh yeah, we have done a lot of numerical experiments, and so here now we have this. Yes, the number of potential facilities from 2 to 40. Then this is the number of parts. Here is gaps, and here is kind of time. And sometimes we just stop. For a little larger problem, we just stop, and this is kind of the optimality gap. It's not too bad. Could be as high as like 8%. For some cases, 13%. Yeah, that's the highest one. So it can have pretty large part gap. But so far we can usually we can only solve problems with good quality and with reasonable time when the number of parts is less than 50. Otherwise, the gap will be pretty large. So actually, we also did a case study So just look at 14 U.S. Marine bases. So yeah, in the United States, there are 14 U.S. Marine bases. And so we try to look at 6 options. The first option, yes, basically we use our model and find the optimal kind of configuration. And with optimal source, right, we just decide where we should have AM capacity, how many machines we should have at each location, and also for each part, whether we will get it and hold inventory, or we just print them out when they are needed. And if we decide to print it out, then where should we print that specific part from which facility with AM capacity. So scenario 2 is called complete centralization. So we just decide that we only have one facility to house all AM machines, and yeah, but we of course still keep inventory as one option. And the complete decentralization means that we have one AM machine everywhere. So each facility will have one AM machine. And also the scenario, the fourth scenario is complete centralization with sole AM supply. So all parts actually are printed out when they are needed, and we don't hold any inventory. And scenario 5 is complete decentralized, and also we don't have inventory. And the last scenario, basically, we don't allow AM. So these are the 6 scenarios we investigated for this case. So here are just the solutions for all these 6 cases. So we have like 14 bases. You can imagine that of course these are marine kind of bases. They are all at the coast, and either east coast or west coast. So that's kind of the scenario when optimal solution. By nature, we will have like 2 locations with AM capacity. So you can imagine that the demand from the west coast will be met by the AM capacity with 2 machines at Maremma, and for the east coast demand, they are all met by 3 machines at Washington D.C. So that's kind of the optimal solution. For scenario 2, it's centralized system. We just only allow like 1 location to have AM capacity. So that's kind of the location. So here, decentralized system, we have capacity everywhere. And also, that's one scenario 4. We just have AM capacity, and we don't allow inventory actually options for any part. So in that case, we need a lot of AM machines. So 8 AM machines at the DC base. So kind of we just have the solutions for all these 6 scenarios. Here is kind of the solutions. So you can see that how many machines we need. And in that case, we need 23 because we do not allow any inventory, right? And then talk about how many parts actually are produced by 3D printers, then the traffic intensity, the average traffic intensity across facilities with AM capacity, then average waiting time, and only this case is terrible with a very long kind of waiting time because we only allow 1 facility having AM capability. So definitely for West Coast, it will take a lot of time. And then also that's kind of the deviation from the optimal solution because scenario 1 is the optimal solution. So you can see that for other options, sometimes the cost will be much higher. So we also did some sensitivity analysis, right, to have look at basically 2 things. One is more about the AM machine kind of cost, the fixed cost for having AM machines. And so you can see that when if we can decrease the AM machine cost by percentage, we will have more machines in total, and also the cost will go down. And here again, we have looked at the build speed. And if we increase the build speed, so if we can print out the things faster, if we have look at, first of all, when we improve the efficiency of AM machines, at first we will assign more parts to AM options, and actually we will buy more AM machines. But if later, actually it will also go down, because when AM machines are very, very efficient, then for US Marine, right, they don't need so many machines. But still keep it in mind, we only talk about 50 parts. Of course, Marine has much more parts that they need to worry about. And so also, you can have a look at the cost. So actually, the whole study, the motivation was that a while ago, I talked to a defense logistic agency. They basically were asked by Air Force and Army and also Navy to look at what parts should be considered for AM. So they basically had no idea. They told me that they have like a database with millions of parts. So they kind of randomly select like dozens. Then they do experiments, take out this kind of perhaps 20 or 30 parts, then get the CAD files and print them out. So they spend perhaps 1 or 2 years just to print them out to see whether they can do it or not. So at that time I asked them, why you choose this 12 or 20 parts and investigate whether they are suitable for AM? They said we didn't have no idea. They just randomly selected. Then kind of that discussion motivated this piece of research. So we say, oh yeah, we perhaps need to worry about that, and especially not only from the mechanical engineering viewpoint, but also from the business viewpoint, which part is more kind of suitable for the AM option. And then second one is what kind of capacity we should have for AM and where we should deploy AM kind of capacity. That's also why we use US Marine as a case for this study, because my dialogue is, I talked to, I think, Air Force before, talked to Navy and also defense logistics agents. And so that's why there are a lot of military kind of background, because they are big fan of AM technology. So just give you a little bit more background of why we do this research. So here we kind of for both parts, we focus on first of all low volume demand products. If you talk about high volume products, I don't think our models actually fit very well. So we really talk about perhaps spare parts, and we have already built mixed integer nonlinear programs for both problems, and then also based on the model kind of property, we developed some exact solution algorithm to solve it, but also develop some heuristics. And so we really have looked at AM machine kind of capacity, because that's also one big concern for many companies. No matter, for a smaller company with just one location, or for larger enterprises with a network of facilities. So as I mentioned, we have talked to them, and so hopefully those kind of models can help them make better decisions to select the parts for AM. So also for both studies, we also have looked at managerial kind of insights to say, if we want to take advantage of the AM technology and want to promote AM adoption, so what kind of improvement we need for the technology development, and also from what kind of viewpoint? Because for users, of course, they really worry about the cost, but for OEMs, they also worry about their revenue, and these two things may not be aligned very well. They can complicate. So they may have different kinds of preferences in technology development based on our kind of sensitivity analysis. I think that's all for my talk, and thank you so much for your attention. And also, I'm from University of Tennessee, and it's we call it Big Orange, so it's a Big Orange. It's almost springtime, so hopefully we can have we can enjoy this wonderful time and enjoy the beauty of spring. So
thank you very much.
Yeah, thank you
Thank you,
so much.
Dr. Jing. That was an excellent talk about the supply chain problems with additive. So, all right. So now we're opening our floor for questions. So while we're waiting for folks to speak, either unmute. So if you wanted to ask a question, either unmute yourself, or if you wanted to use typing, please feel free.
Let me just thank Dr. Jin. I have known him for several years.
Yeah, we haven't known each other for a while.
He's a fantastic researcher, a great leader. I actually joined the logistics supply chain division while he was the president as well, and fantastic. I think this is an excellent work that spans across operations research, supply chain, and AM. So thank you so much for taking time. It's always hard to present your work where sometimes your students have made a lot of inroads on the theoretical side, but then you have to still present the big picture. And we appreciate you taking the time out of your busy schedule. So I'm going to leave it at this point. Of course, we will connect offline, but thank you so much for coming.
Yeah, thank you. It's very nice to see you virtually, of course. Yeah, because I learned
Virtually.
that you moved to Louisville, and hopefully you enjoy it.
Yeah, absolutely. Fantastic place.
Hi, Minzhou. This is
Mhm.
Li Hui. Glad to
Okay.
hear about your talk. You know, we know long time and never came across that you're working on something similar in some aspect. Just want to share that myself and Dr. Yang, we were working more towards the simulation model on the additive manufacturing side, and then how that and different manufacturer settings can affect, the production rate and the quality, reliability, and all that. And then currently the model, we just use some basic, stochastic inventory safety stock parameters to evaluate what would be the alternative inventory route. One is what we call the AM route. The other is the inventory route, which is using traditional warehousing. So it's good to see that you're actually delve deeper into the modeling for the inventory, where we were focusing a lot on the AM side. So it's nice to see the compliment. Good to see you.
Yeah. So yeah, of course we have known each other for many years. I don't know how many years, 15 or 16. I don't know. Yeah. So you're definitely right. Okay. And here, yeah, we also develop a very simple simulation model before. Okay. Basically, my students did it. I was not so involved for this problem. And another thing about the quality. You mentioned quality. Quality is a big concern. Of course, we are doing several other projects just for quality. For this model, we originally actually had quality in the model because you're exactly right, Dr. Pai. The quality actually has an impact on reliability, right? So the quality will have an impact on the demand rate. I don't know. My co-author from business school, they are so different. I should not complain, okay? Because first part we want to, we try to submit it to some good journal, right? Like PALMS or Amazon. We try to engage some senior editors over there, and he's a co-author. And he doesn't like that part. I argued against him for so many times, and he's too busy. Just that paper can never be submitted. I don't know why. So we actually submitted the second paper already, not the first paper, because then I decided not to have him as a co-author as the second paper. Yeah. But I completely agree. Quality, reliability should be modeled there. Just he doesn't like it, then we delete it. It's kind of fun. I don't know why.
Yeah, it's very interesting. I didn't know about this background story, but I mean, to me, I was going to actually ask you about the quality part because, so far most of our what we hear from the supply chain talk with additive is about quality control. It's about process, materials, feedstock, everything. So quality is, of course, a big part of it. So I was going to ask you how is that going to be integrated in like a traditional supply chain model?
Exactly. We basically did it, right? So basically we changed lambda. So if you use AM, the quality will be worse, then the demand rate for that part will be higher. That was our original work. We finished everything. Then that colleague basically said, oh, for those kind of journals, people don't like to have too many things and don't mix all kind of things. He's an expert, definitely a very wonderful expert for inventory management kind of things. He said, yeah, I don't want to have quality. So we delete all quality kind of things. Yeah. I still personally don't agree with that, but what can I do?
One thing that might help you is try to find some more manufacturing-oriented journal that will pay more attention to quality. You know, for the journal publication we had, because it was heavily on the AM side, so it didn't fare well with ISC transactions. So when we turn into you know, a rapid prototyping journal, it was very much appreciated, much better appreciated. So I guess it's where you angle. Yeah.
Yeah, the second part is under revision for ISC transactions actually. But the first part we would like to try, you know, Amazon or Palm. That gave me trouble. And he's a senior editor for both, so what can I do? You know, the department editor actually. Yeah. I don't know. Already like 5 or 6 years. So, you know, it's a long time. And they're from business school. They can wait. They don't really worry about the time. We're from engineering, right? It's pretty different kind of philosophy, right? For them, okay, it's okay. 2 or 3 years, no problem.
So I think I have another quick, well, maybe it's not too quick, but another question is, you know, the kind of the hope that I always have from the perspective of additive people is that, you know, we've been dealing with the kind of mindset that says cost is everything in manufacturing, and so that is part of the reason why we have such a fragmented supply chain, totally decentralized, and you know, worldwide kind of supply chain that is not very responsive. So what's your thought about, you know, utilizing this kind of model to convince people that the other components except for cost is also playing a very important role in additive?
No, actually, it depends, okay, whom you talk to. So we have projects for Y12. Y12 is, you know, a manufacturing facility for DOE. And we have already worked with them for many years. My student, Jeremy, works with them on some SLM machine mainly for quality. We try to talk about cost. They never care about cost, okay? They have too much money. They don't care about cost. They don't care about cost at all. Okay, when we talk about cost, they say, no, forget it. So if we have look at Jeremy's work, nothing about cost, nothing about cost. They just say, oh, we want to just produce things. For what? I even don't know for what. Okay, they just need to do it. Okay, and we work on all kind of things like laser calibration, oxygen level. Also, yeah, now work on like, okay, machine kind of monitoring, but nothing is cost driven. Nothing is cost driven. And you know, I don't exactly know why they do that. They produce a lot of things, but they never use them. They just want to do it, okay? And they don't worry about the money at all. So that's okay, Y12. But similar things, sometimes even for some larger companies. And they also do not necessarily really cost driven. But for small businesses, they are so cost sensitive. But they hesitate. They enjoy all kind of workshops, you know, for all those workshops. They come, listen, and want to learn something more, but they don't want to make investment because they are worried about the cost. So yeah, for your question, it's a wonderful question, but it really depends who is the audience for our research. We need to be very, very careful. You're right, for our kind of IE traditional community, we really worry about the cost. And even when we talk about quality, we sometimes try to connect the quality, right, to the cost term. But that's not necessarily the mindset for some people, especially for manufacturing kind of community. It's just a little bit different perspective. I don't know. They don't, based on my interaction with them, they don't talk about the cost so much.
Yep, I think the perception in the community, in the additive community, is still that additive has so much functional advantage, so much performance advantage that cost is not really a factor. But at the same time, you hear a lot about sustainment, about replacement of the exact old parts that no longer even exist. So,
Yeah.
I mean, the cost is playing an important part for their decision. Of course, there's the obsolescence of the the lack of original supply chain. They no longer have the original part supply, so they have no other option. But it's a mentality. I think this is something to do with mentality that they have they have not entirely appreciated that cost is going to be part of the big factor, just like any of the other manufacturing processes. It's just that we might need to look at it not just from the cost of additive operation, but at the entire supply chain, at what you included in there, which is impact downstream, or the what would incur if the part is not delivered on time, and that is unfortunately out of equation from most companies. Like when we talk to a few other aerospace companies, they had the same issue that their additive people was like talking about, I don't care about the basically I don't care about the cost of this part. It cost $5,000, but you don't have any other options, because if we don't make this out of additive, there is a grounded aircraft, and that's $10,000 every day. And then from the supply chain's perspective, they don't care. They're like, okay, why am I getting this part 10 times as expensive as I can from the other sources, with maybe roughly a 1 or 2 more day of lead time? And I think there's a lot to catch up.
That's right. Yeah, I completely agree. Yeah. That's what I have already seen through my interactions with those companies. Also, more with kind of government agents. Their mindsets are very different, I would say.
Yep. That's I guess we're talking about two different words.
Yeah.
That we're asking for money, and then they're willing to throw money away for no reason.
Sometimes they do that. I have to say that. It depends. Sometimes it's very hard to get money, but sometimes I don't know why they spend so much money.
Yep.
Extra money.
All right. Looks like we have some other questions coming in. Oh, it's not a question. It's a comment. Really appreciate the discussion. All right. I guess for the sake of time, we'll wait for Joseph's question here, and if there is any other quick question, I think it's the perfect time to unmute. All right, so we don't have a question coming in here. So is there any other quick questions that our audience wants to ask before we wrap this up? Okay. All right. So I think with that, I think that's the end of our seminar for today. And if you have any further questions, please feel free to direct it to either myself or Dr. Jing himself. So, like I said, he was perhaps one of the only few experts that actually understands about the numbers in this area. So definitely feel free to send him an email to any questions for any questions you might have. Thank you very much. Really appreciate your taking time and talking with us today, Dr. Jing.
Yeah, thank you so much. Thank you all, and have a good weekend.
Thank you. Have a good rest of the Friday afternoon.
OK， 那谢谢，就你可能还在 record。
我看一下我能不能停止不是我录的，哎，是那个另外一个录的，它好像没有停止。哦，我可以停一下。